Our universe is a place of constant change and transformation. Nowhere is this more evident than in the realm of radioactive elements. These elements possess an inherent instability, a restless energy within their very core. This instability manifests as radioactivity, a phenomenon where atoms spontaneously emit particles and energy. Radioactive elements are not merely scientific curiosities, they are found everywhere, from the rocks beneath our feet to the distant stars in the night sky. They are even present within our own bodies, a testament to the interconnectedness of all things. The discovery of radioactivity in the late 19th century revolutionized our understanding of matter. It revealed that atoms, once thought to be indivisible, were themselves composed of smaller particles. Moreover, it showed that these particles could be ejected from the atom, transforming one element into another. This process of transformation, known as radioactive decay, is the key to understanding the nature of radioactive elements and their profound impact on our world. It is a process governed by chance, yet it unfolds with a predictability that allows us to trace the history of our planet, diagnose and treat diseases, and even harness the immense energy within the atom. To comprehend the essence of radioactivity, we must delve into the heart of the atom, into the realm of protons and neutrons that constitute the atomic nucleus. Stable atoms exist in a state of equilibrium, their protons and neutrons bound together by the strong nuclear force. However, certain atomic nuclei possess an imbalance in this delicate dance of forces. These unstable isotopes, as they are called, are like ticking time bombs, destined to transform themselves into more stable configurations. The concept of half-life provides a measure of this instability. It represents the time it takes for half of a given sample of radioactive atoms to undergo decay. Imagine a group of 100 unstable atoms. After one half-life, only 50 remain in their original form. After another half-life, that number dwindles to 25, and so on. This process of decay is exponential, meaning that the number of atoms decaying at any given moment is proportional to the number of unstable atoms present. It is this fundamental principle that allows us to use half-life as a clock, a way to measure the passage of time on scales both minute and vast. Radioactive decay is a symphony of transformations, each emitting different types of radiation. These emissions are alpha, beta, and gamma radiation. Alpha decay ejects a helium nucleus, reducing atomic number by 2. Beta decay transforms a neutron into a proton emitting an electron or positron. Gamma decay releases high-energy electromagnetic radiation. Understanding these interactions is crucial for various applications. The concept of half-life might seem counterintuitive at first. If radioactive decay is a random process, how can we predict when half of a sample will decay? The answer lies in the sheer number of atoms involved. Imagine flipping a coin. The outcome of a single flip is unpredictable. However, if we flip millions of coins, we can confidently predict that roughly half will land heads up. Similarly, while the decay of an individual atom is unpredictable, the behavior of a large collection of atoms becomes statistically predictable. This statistical predictability arises from the law of large numbers. With a sufficiently large sample size, the random fluctuations in individual atomic decays average out, resulting in a consistent and measurable rate of decay. This is why we can confidently state that half of a sample of carbon-14 will decay in 5,730 years, even though we cannot predict which specific atoms will decay at any given moment. The concept of half-life allows us to bridge the gap between the randomness of the quantum world and the predictable behavior of macroscopic systems. It is a testament to the power of statistics to reveal order in apparent chaos. Section 5. Measuring time's arrow, the mathematics of decay. The concept of half-life is not merely a qualitative description but is rooted in a precise mathematical framework. This framework allows us to calculate the amount of radioactive material remaining after a given time or to determine the age of ancient artifacts. The fundamental equation governing radioactive decay is Nt equals sign n 0 asterisk 1/2 Tt, where Nt is the number of atoms remaining after time Tn 0 is the initial number of atoms. T is the elapsed time. T is the half-life of the radioactive isotope. Let's consider an example. Suppose we have 1 gram of carbon-14 which has a half-life of 5,730 years. How much carbon-14 will remain after 11,460 years? Using the equation we get Ne 11,460 equals sign 1 asterisk 1/2 11,465,730 equals sign 0.25 grams. This calculation tells us that after 2 half-lives, only 0.25 grams of carbon-14 will remain. This simple yet powerful equation forms the basis for various applications, from dating ancient artifacts to monitoring radioactive materials in nuclear power plants. Section 6. The alchemy of atoms, factors influencing half-life. The half-life of a radioactive isotope is not fixed. It can be influenced by various factors. Internal factors include nuclear configuration and energy levels. External factors like temperature and pressure also play a role. Understanding these factors is crucial for applications in nuclear medicine, astrophysics, and environmental science. Section 7. From ancient clocks to modern medicine, applications of half-life. The concept of half-life is crucial in various fields, from dating artifacts to diagnosing diseases and generating energy. Radiocarbon dating reveals the age of ancient remains. Medical tracers diagnose conditions. Technetium-99m is used in imaging. Nuclear plants use decay energy. Understanding half-life ensures safety and efficiency. Half-life impacts archaeology, medicine, and energy. Section 8. A universe of elements, the diversity of half-lives. The periodic table is a testament to the diversity of elements in our universe, each with its own unique properties. This diversity extends to the realm of radioactive isotopes, where half-lives can range from fractions of a second to billions of years. The half-life of an element is intrinsically linked to the stability of its nucleus. Elements with very short half-lives, such as those found at the bottom of the periodic table, are highly unstable and decay rapidly. These elements are often created in laboratories using particle accelerators and exist for only fleeting moments. On the other hand, elements with long half-lives, such as uranium-238 with a half-life of 4.5 billion years, are relatively stable and decay slowly. These elements have existed since the formation of our solar system and continue to shape our planet's geology and climate. This vast range of half-lives reflects the delicate balance of forces within the atom. It highlights the intricate interplay of fundamental constants and the profound implications of even minute differences in nuclear structure. Section 9. Dispelling the myths, half-life misconceptions. The concept of half-life, while fundamental to understanding radioactivity, is often surrounded by misconceptions. It's crucial to dispel these myths and to foster a clear and accurate understanding of this important concept. One common misconception is that the half-life of a radioactive substance indicates its hazardous nature. While it's true that isotopes with shorter half-lives generally emit radiation more intensely, the overall danger also depends on the type and energy of the radiation emitted and the amount of exposure. Another misconception is that radioactive materials remain dangerous forever. In reality, the radioactivity of a sample decreases exponentially with time. After a sufficient number of half-lives, the remaining radioactivity becomes negligible. It's also important to remember that radioactivity is a natural phenomenon. We are constantly exposed to low levels of background radiation from cosmic rays and naturally occurring radioactive isotopes in the environment. By promoting scientific literacy and dispelling these myths, we can foster a more informed and nuanced understanding of radioactivity and its implications for our world. Section 10. The enduring legacy of half-life. The concept of half-life, born from the study of radioactivity, has transcended its origins to become a fundamental principle with far-reaching implications. It has provided us with a clock to measure the vastness of time, a tool to unravel the mysteries of the atom, and a means to harness the immense energy within the nucleus. From dating ancient artifacts to advancing medical treatments, from monitoring environmental changes to exploring the cosmos, the applications of half-life are as diverse as the elements themselves. Understanding half-life is not just about memorizing equations or definitions, it's about appreciating the intricate dance of forces within the atom, the interplay of chance and predictability, and the interconnectedness of all things in our universe. As we continue to explore the frontiers of science, the concept of half-life will undoubtedly continue to guide our understanding of the universe and our place within it. It serves as a reminder of the constant change and transformation that characterize our existence, a testament to the enduring power of scientific inquiry to illuminate the wonders of the natural world.